Hello. Today we are going to talk about economic growth theory, which is the first macroeconomic model we will discuss in this macroeconomics class. So what are we going to do today? First of all, I will give you some motivation. What is growth theory about? Secondly, we talk about an aspect which is called growth accounting. And finally, we also discuss the famous model in growth theory, which is the Solow model. So let me start with motivation. What is growth theory about? Well, first of all, growth theory studies the long-run behavior of an economy. And we will discuss question of what is determining this long-run economic growth. Why are some countries growing faster than others? Why is the growth rate at the moment in China very high, in Germany very low? Will there be a kind of catching up of emerging economies to industrialized economies? Why are some countries richer than other countries? So these are all questions we try to address in economic growth theory. So we care not about these ups and downs, the booms and recession here. We care more about the long run growth trend. And long run means, well, this is growth over 20, 30, 40 or 50 years. Why is long run economic growth so interesting? And why are economists talking about growth in general? This has to do with the simple insight that economic growth is linked to the standards of living. So the higher the economic growth, the higher the GDP, and we have talked about in a previous class, the higher is the income of the overall economy and the higher is the income you have. And therefore, growth is very important to increase the income and the standards of living. So let's take a look to growth here. I have a graph of 4 countries, European countries, France, Germany, Italy, and the United Kingdom, from 1950 to 2010. And what you can see by looking at this graph over this time horizon is, well, that all the countries have grown in economic terms. So what we have here is GDP growth, which is the growth of the gross domestic product, the values of goods and services these countries have produced. And you see they are growing. But we can also see, interestingly, the red curve is Germany. Here the growth rate was faster than the growth rate in the other countries, Italy, France, and UK. And one question obviously is, why has Germany grown faster after, so around the 1970s and so on, than countries like Italy and France? And we will obtain an answer. We will get an answer by studying growth theory in more detail. Let's take a look to another aspect of growth theory. Here, this is a graph with many countries. Each dot here is one country. And there are 2 variables. On the horizontal axis, we have GDP per capita, which is the income per head in these countries. And on the vertical axis, we have life satisfaction, the happiness of the people in this country. And what you can see now is the higher the income you have, the higher is the life satisfaction, the more happy are the people in your country. So you see there's a positive relationship, and that is indicating by this black dashed line between GDP level. The higher the income, the higher the GDP, the higher is the happiness, the higher is the life satisfaction. That is what I already mentioned. Why growth theory is so interesting from economic point of view. Because GDP growth is linked to happiness, is linked to the standards of livings. The higher the income, the higher is the life satisfaction. And that is one motivation to look closer to this phenomena and to understand what is driving GDP growth. So if the policymaker is able to stimulate the economy towards GDP growth, that is good for the society. It's good for the population in this country. Now let's take a look to growth theory from a longer term perspective, looking back over 2,000 years. So here I have a graph that starts in 0. Yeah, it starts from Christ, the birth of Christ, until today, the year 2000. So it's a very long-term view of economic growth. And there's some interesting pattern in this graph. So the growth at the beginning and the income per head at the beginning in year 0, well, this is here computed with a number of around 460. The number does not matter. But the interesting point is the following, that this stayed almost the same until a year around 1500. And even in 160 and 170, it's very similar. So it seems to be for more than 1,000 years, or 1,500, 600 years, there was almost no GDP growth. The income remained at the same level. Yeah, it remained at the same level. And then something happened out of the sudden around this period. And you can see then the income increased exponentially. So what has happened here? What has changed this behavior over 2,000 years? Well, what has changed this is the Industrial Revolution, the development of the steam machine, first Industrial Revolution. And then the second Industrial Revolution, development of engines. And you can say the third wave of Industrial Revolution is the computer age, the mobile age, and so on. This has driven economic growth to very high levels, to this exponential increase of GDP. And there's a second factor that has or have contributed to this behavior. And that is indicated by the size of these green dots. And you see the green dots are increasing also here at the end here. And that has to do with population growth. At the beginning, the population growth was almost the same in every generation. There was not really a large population growth for centuries. But then, with the Industrial Revolution, this has changed. And this is indicated by the size of these green circles. So the interesting insight from this graph is, keep in mind that we are living in an unprecedented time of GDP growth. But that is GDP growth that just appeared over the past 200 and 300 years. Over centuries, over thousands of years, this was not the common issue. So it's quite interesting to learn a little bit more and to get an understanding. Why has this happened? What is the impact of industrial revolutions to our GDP growth? And that is actually what we try to study in growth theory, to get a better understanding. How can we stimulate GDP growth in the long run, that this beautiful behavior and pattern we can see from this graph continues as long as possible? And now I have a final table to motivate growth theory. So if you take a look to this table, you see once again countries like France, Germany, Italy, Ireland, Japan, Netherlands, UK, and the US at the bottom. And I have highlighted here two countries, Germany and the US. The numbers are GDP growth rates in average over 10 years, over a decade. So the 1960s, the first column. Then the average growth rate in the 1970s, in the 1980s, here in the 1990s, and the last column is the average growth rate over the whole time horizon, from the 60s to 2000. What is interesting to see is the following. First of all, in the 1960s, GDP growth rate in average was around between 4 and 5 and 6. Yeah, so Germany was 4.2, in the US it was just 2.3, but most of the countries had numbers around 4-5%. If we compare the growth rates in the 60s with the growth rates in the 90s, well, you see immediately the growth rate in the 90s were far smaller. So here the growth rates in average, you would say, well, they were around 1.5%. So there is a clear decline in GDP growth rate from the 60s to the 1990s. And you can see this from decade to decade, that the growth rates declined from every decade to the next decade. And that is an interesting question. Why do we have this pattern that at the beginning, in the 60s, there were high growth rates, and now we have lower growth rates? Growth theory will give an answer, and we will learn the answer of this pattern. There's a second interesting information in this table. So if we compare Germany and the US, we see that Germany had a far higher growth rate in the 60s than the US. Also Italy, also Ireland, also France. What could be an explanation of this? Well, we will learn the explanation. This has to do with the Second World War. After the Second World War, most of the European countries were destroyed. And so the catching up phenomena, so the GDP growth after the Second World War, were very high. So there's a kind of catching up phenomena in growth theory. And therefore these countries grow very fast in the beginning after the Second World War, while the US was not so much damaged by the Second World War. And therefore the catching up phenomena is far smaller, or was far smaller in the US. If we look now to the growth rates again to the 1990s, you see now the European countries have catched up to the US. And the growth rate now in the European countries is quite similar to the growth rate in the US. So you see there are some interesting information in looking to GDP growth rates. And what we are going to do now in the next chapter is to explain this pattern we see over time and we see across countries in a consistent economic model. It's the Solow growth theory. Okay, so let me sum up the motivation of the first part. So in growth theory, we will study the long-run economic behavior of an economy. We will talk about why countries grow faster than others, why countries are rich and why others are poor. We will talk about this catching up phenomena. Why do we have some countries at some point of the time higher growth rates like China of today, and other countries lower growth rates like Germany today? And once again, let me make clear a very important point. In growth theory, we are talking about the long run and not the short run. So another way to illustrate this in a graphical sense is by taking a look to the business cycle. You know, usually economies have these ups and downs, booms and recessions. But this is a very short run view to the economic development. In growth theory, we don't care about these ups and downs. In growth theory, I am interested in the long-run average trend of this country. And you can see that the ups and downs are circulating. They are moving around this long-run trend line, this line. And we try to explain what is determining the slope, the factors that this line is upward sloping, that countries are growing in the long run. So we will talk about the factors that have an impact on the long run growth trend, this line, and that is the message of growth theory. It's not about these ups and downs. This is discussed in business cycle theory. That is another lecture. Okay, so now let's talk about what we call growth accounting. So first of all, we look now to the factors that have an impact on GDP growth. And the key factors, they are linked to the production function you have learned in a microeconomics class. What are the elements in a normal production function? Capital and labor. The more labor I have, the more capital I have, the more I'm able to produce. This is what you have studied already in an economics class. And it's the same here in growth theory. Capital and labor are the two most important and relevant input factors. But we will see there is a third one, which you have not included in a production function in a microeconomics class or an economics class in the beginning. And that is productivity or technology. And for technology, we introduce a new variable, an A. For capital, I use K. For labor, I use L or N. And now what we can do is we can discuss the different components of growth by computing the total differential of the production function. And you can see this from my slide. Well, what I did here is I computed the total differential of the production function in respect of all the three components. First, I compute the partial derivative of the production function in respect of capital, which is reflected in the first component on the right-hand side. Then I compute the derivative in respect of labor, the second component. And then I compute the derivative in respect of technology, which is the last and the third component. And then I simplify these three components in the end, because what I can show you here is that the partial derivative is nothing else as the growth rate. So what we have on the left-hand side is the growth rate of GDP is then equal to the growth rate of capital, the growth rate of labor, plus the growth rate of technology, the third component. So in other words, we can split up the GDP growth rate, the growth rate of the overall economy, into three growth rates, into the growth rate of capital, growth rate of labor, and growth rate of technology. And that is what we call growth accounting, splitting up the GDP growth rate in these three growth components. The question is, what is behind these three growth components? Well, growth in capital means investments in firms, in factory halls, in machines, equipment. Growth in labor is, well, it's growth in the growth of the workforce or population. And growth in technology, well, this is investments in education, in R&D, research and development. Now let's take a look to these three growth components from an empirical point of view. Here you can see a table, and this table you see for Germany the potential growth rate over time. It starts from a period 1996 to 2000, from 2001 to 2005, and so on and so forth. And the first column of this table is illustrating the potential growth rate, the long-run growth trend in this time window. And then in the next columns, you can see the different components. Capital, so what is the contribution of capital growth, labor growth, and technology growth? And there is an interesting information in this table. First of all, the contribution of labor to the overall potential growth rate in Germany is negative. So the population growth, in other words, has not contributed to our overall GDP growth. And this has to do because Germany is an aging society. So the labor force is shrinking. And therefore, the contribution of labor in Germany is negative to GDP growth. But we can see another interesting part. The contribution of capital and the contribution of technology is positive. And that is the most important finding in this table, the biggest contribution of potential GDP growth in Germany is coming from technology and not from growth in capital. The capital growth rates are large, but the growth contribution of productivity, of technology, is even larger. And we will see this when we discuss the Solow model, that technology is a key growth factor in the long run. And if we want to sustain economic growth, we have to incentivize technology and productivity. Okay, now let me start with the model. The model is called the Solow growth theory. Well, it was developed in 1956 by Robert Solow together with Swan, but Solow got the Nobel Prize for this development in 1987. Robert Solow was a professor of economics at MIT, and he was born in Brooklyn in New York in 1924. And he has really invented this whole field of growth theory, which is currently in place in macroeconomics. So what are the questions he addressed with this model? First, he asked, what are the fundamental factors of economic growth? We already talked about the key factors. It could be labor, capital, or technology. And we will see that technology is a major factor. And he also asked, how does economic growth evolve over time behind this growth pattern? And he asked the question, why are some countries poor and the others rich? Okay, the growth theory consists of 4 elements. The first element is a production function. The second element is an assumption we use in the beginning here to make it as simple as possible. And that is a closed economy. In a closed economy, you have learned in one of my first classes in macroeconomics, we have the identity of saving is equal to investment. The third building block, an assumption, is a saving function. And Solow assumes that the saving is dependent on the income. The larger your income, the more you are saving, which makes intuitively sense. And he assumed that the proportion of saving is constant. It's a marginal propensity, and this is constant and given. Also, this assumption is a simplification because in reality, people also change the saving behavior over time. And you can extend the Solow model to an open economy, and you can extend the Solow model to a saving function, which is more realistic. But we will start with a very special and very simplified version of the growth theory to see the bottom line of this model. And the final and fourth assumption in the Solow model is what we call the capital dynamics. And you can see these 4 assumptions from my slide. Well, let me explain first of all the condition 4, because this is the most complex and new for most of you. The capital dynamics consists of 2 sides. On the left-hand side, you see the K, which is the capital stock in period T, KT. And above this variable, there is a little dot, and that is reflecting the time derivative. That means it's the change of the capital stock over time. So on the left-hand side, again, let me repeat, you have the change of the capital stock over time. This is the time derivative indicated by the dot. And then on the right-hand side, you see what is driving the change of the capital stock over time. The first component is investment. The larger the investment, the larger will be the increase of the capital stock over time. So it's positively linked to the change of the capital stock. And the second component on the right-hand side is what we call the depreciation of the capital stock. And there's this delta, which is the so-called depreciation rate, times the capital stock in period T itself. What is capital depreciation? Well, suppose you have a factory hall. At one point, this factory hall is new. But over time, obviously, this factory hall gets older and older. And that is reflected by capital depreciation. And therefore, we subtract this component from my investment because depreciation is lowering the change of my capital stock over time. So this is overall what we call the capital dynamics. The capital dynamics reflects the change of the capital stock of the left-hand side, and it's determined by the components on the right-hand side. Investment, increase the capital stock, and depreciation, decrease the capital stock. Let me give you now a brief recap of the production function. Probably you're all familiar of the production function from an introductory economics class or a microeconomics class. The key properties you should keep in mind are 2. First of all, the production function is always a concave function. That means the larger the capital, the more is the production output. So the first derivative of the production function is positive. But the second derivative of the production function is negative. This is the law of diminishing returns. That means the additional contribution of capital gets less the more capital I have. So keep in mind these 2 properties. First derivative is positive of the production function. Second derivative is negative. This is called the law of diminishing returns. You all have heard about in an economics class. Now, to derive the Solow model requires a further discussion. I already showed you that we want to compare, in the end, the growth rates across countries. So we want to understand why are some countries growing faster than others. So if we want to do a comparison, we have to define a common ground, a level playing field. And one way to define this level playing field is to divide and norm all the countries to a certain common level. What is this common level? Well, I would say the common level is we have to look to the contribution of one human being. So in other words, what I'm going to do, I divide all my variables by the number of people or the population size in a country. Why I'm going to do this? Well, suppose we have two countries, Germany and China. In China we have 1 billion people. In Germany we have just 80 million people. It's obvious that 1 billion people can produce more than 80 million. The more people I have, the more I can produce, cars or whatsoever. So it does not make sense to compare these two countries if they have different sizes of the labor force. And therefore what I'm going to do, I divide my output in respect to all the people. That is what we call output per capita or output per labor. And I also divide my capital stock I have by the number of people. That's what we call this the capital labor ratio. So what I'm looking at in the end is by looking to the variables of per capita, output per labor, capital per labor. And I'm looking to and study what is the impact of one individual to the overall economy. And if I have these variables, then I can compare the growth in Germany with the growth contribution in China, because I want to understand what is the different growth contribution of a single human being, and not because I have more human beings in China or people and less in Germany. So in growth theory, once again, we are studying per capita growth rates. So let me write down, to repeat what I already said and to keep in mind, the 3 building blocks of the Solow model. The first building block is a production function. So y is my output variable in time t. And this consists of technology A and the production function f dependent on capital in period t and labor in period t. The second component is the closed economy assumption. And closed economy, as we have learned in my first macroeconomics lecture, implies saving in period t is equal to investment in period t. The third building block of the Solow model is the saving function. Saving in period t is dependent on my income is y, times a certain proportion, s, of my income. So suppose you have 100 euros, then you save, let's say, 10%. So the s is then 0.1. That's what we call the propensity of saving times income. 10% times my income 100 gives me 10 euros, which I save. And the last condition, the fourth condition, is the capital dynamics. So it's a change of the capital stock over time indicated by this derivative. That's the first derivative in respect of time of my capital stock. And that is determined by the more investments I have, the higher is the increase in my capital stock over time. And the capital depreciation, delta is the depreciation rate times my capital stock, that is lowering the growth of capital over time. Investments increase the capital stock over time, depreciation lowers the capital growth over time. So these are the 4 building blocks of the Solow model. And now what I have to do is, well, I have to transform condition 1, 2, 3, and 4 into per capita variables. By the way, I have a reading which is linked here, which is a paper written by The Economist. And The Economist is really explaining why it's so important not to look at the aggregate variables, why it's so important to look at the per capita variables. And that is what I'm going to do now here analytically. So I transform this model into per capita. In other words, I divide the output or the income by the number of people, L. And I define this fraction with a new letter, the small y, t. So the y is nothing else as the overall income of Germany divided by all the people working in Germany, L. And that is then the output, what we call output per capita. And I do the same for capital. The whole capital stock we have in Germany divided by all the labor we have in Germany gives me the so-called small k, the capital labor ratio. So these are the variables I'm really interested in. And I can do this for the production function here. So if I use condition 1, and if I divide this equation by L, then I have the small y here on the left-hand side. And then the L cancels out here. And you see, then in the end, I have k divided by L here. So what I have is then my A in front. And then I have a production function, which is now the small f, dependent on the small k, the capital labor ratio. So this is the production function, what we call the production function per capita. And it's obtained from this, just dividing this equation by L. Okay, that's fine so far. To study the Solow model in the end, I have to transform now the last condition, this capital dynamics, into per capita variables. And if I have this final condition, then I will stop with the analytical discussion. And I will transform this final condition into a graph. And then we continue with the graphical discussion of the Solow model. That's what usually undergrad students like more. But before I can do this graphical discussion, well, I have to go through some computation. Let's do it. Now I transform this condition into per capita. So in the end, what I'm interested in is in the capital dynamics, not of the capital K, of this large K. I'm interested in the capital dynamics, in the change of the capital labor ratio, in the small k. So how can I compute this? Well, what is this? Well, this is the derivative of the capital labor ratio over time. So let me write down this in words. It's the derivative of the capital stock, or the capital labor ratio, over time. So that's dk dt. That's just another way to write down the kt dot. But what is this small k? How is this defined? Well, this is defined, as we see here, it's defined as the capital stock divided by labor in respect of t. So I use now for the small k the definition. And now what I have to do finally is, well, I have to compute the derivative of this fraction k divided by L in respect of t. Well, this requires some mathematical skills. It requires that you have to remember, well, we have a fraction, so that's a law of fraction we have to use, And we have to use the chain rule because all the terms are dependent on t. So they are a function of t. So the chain rule. We have to apply the rule of fraction combined with the chain rule. So let's do this explicitly here. First, we compute the derivative in respect of k, in respect of t. Well, that's kt dot, and the lt is treated as a constant. Now we have computed the derivative in respect of k, but we do the derivative in respect of t. Well, this is kt dot is the time derivative. The derivative in respect of k is 1. So it's 1 times kt dot divided by lt. So that's it. Now we compute the derivative in respect of L. So we keep the kt as given. That's like a constant now treated, like a constant. And the derivative of Lt, because it's in the denominator, is then minus Lt square. That is the derivative of 1 over Lt. It's the minus comes in front because it's in the denominator. And then we have minus 1 in the denominator, gives me the square term. And then we have to do once again the derivative of L in respect of t, which is Lt dot. That's the time derivative of L in respect of t. Now let me rewrite this term a little bit. First of all, for kt dot, I write down the right-hand side of condition 4, which is investment minus depreciation divided by Lt. Minus, now I split up this Lt square in two components. So it's kt divided by Lt times Lt dot divided by Lt. So you see this is Lt in the denominator times Lt is still Lt squared. I just split it up in two components. That is good. Now let's simplify this line even further. So still on the left-hand side, keep in mind, we have the dynamics of the capital labor ratio, the small k. How can I simplify this even further? Well, from condition 2, the closed economy, we know that investment is equal to the saving. That's a closed economy assumption. Condition 2. And from condition 3, we already know that saving is assumed as the propensity to save times income, YT. So this is, first we use assumption 2, closed economy, saving is equal to investment. And then we use assumption 3, saving is a certain function which is dependent on income times my propensity to save. So in the end, instead of I write down this function, which is the same given the assumptions of the Solow model. So for investment, I write down the saving function S times YT divided by LT, and then the second component is my delta KT divided by LT. This is the second component, and then here minus KT divided by LT, LT dot divided by LT. So I keep the second term as it is here. Okay, take a look to the first term. Here we have income divided by labor. This is output per labor, output per capita. We already defined output per labor with a small y. So what we have here is the saving rate times output per labor, the small yt. Then we have minus del, the depreciation rate. Take a look to this. This is capital per labor. This is what we already defined here. It's the small k. It's the capital labor ratio minus kt. Then we have the next minus. Again, capital divided by labor. It's my small k. This is my small kt. And then we have a term LT dot divided by LT. Well, you might ask, what is this? We have not really talked about this LT dot divided by LT. But I can show you within a second what is behind LT dot divided by LT. Okay, so let me explain what is LT, the change of the population, the LT dot over LT. So what is that? It turns out that this is nothing else as a population growth rate. So let me talk about the definition of population growth rate, and then you will see immediately that this is the population growth rate. So in general, you would say the population growth rate, let's call it N, is nothing else as the change of the size of the population over time. So it's the size of the people, the number of people in period T, minus the number of people in period T minus 1, so in the previous year, divided by the people in the previous year, L in period T minus 1. This is a normal way we define a growth rate. It's a rate of change. People today minus the number of the people in the previous year divided by the people in the previous year. But here we have 2 years. Year 2014 minus year in 2030. Now assume that the time period is not a year. It's maybe a month, or it's a day, or it's an hour. So if we make this time period very small, yeah, you can say it's a change of number. It's a delta L divided by L. So we make this time period very small. So it's a delta. And if the delta is even smaller, it's not just a day, it's not an hour, it's not a second, it's a millisecond, it's even less, then the delta turns into the derivative. And the derivative is a dot. It's a time derivative. So a time derivative is a small change of the number of people over time. So LT dot divided by LT is in nothing else as the population growth rates. And that comes from this definition and from the approximation that the time is very small we are looking at. So in other words, for LT dot, the change of the people divided by the people, we can use the letter N, which is the population growth rate. So back to my equation we talked about. So for this term, for this fraction, LT dot divided by LT, we now write down N, which is the population growth rate. So now let me simplify this term here a little bit. On the left-hand side, again, we have KT dot, which is the capital labor ratio over time. Then the first component is my saving rate, S. This Y is the income per capita, which is the income per head, income per person. And that is determined from my assumption 1, from my production function. This is the production function per capita. So I can write down the F, and this is dependent once again on my capital labor ratio. Then I have minus two components. Take a look. Both components consist of k. So let me factor out the k here. So then I have minus n plus delta times k. Can you see that this is the same? It's minus n times k, the last component, and minus del times k, the second component. So this is completely the same. I just factored out the k. And this equation now is the dynamic equation of the Solow model in a per capita version. So all the variables, as you can see, are now the small variables. The capital labor ratio, the saving rate, population growth rate, and del, the depreciation rate. So what we have done, we have transformed the Solow model, the four conditions I started with, into a per capita version. And now what I'm going to do at the end of this derivation, I will transform this equation here on the bottom into a graph. I will divide the derivation in two parts. First of all, I will take a look to the second component. I will call this a depreciation component because we have the depreciation rate here, and I will illustrate this in red. And I will look to the first component, and I will illustrate the first component in blue. So what is the graph we are now drawing? Well, we have a graph, and on the horizontal axis, on this one, we plot the capital labor ratio, the K. On the vertical axis, we plot the output per capita, the Y. So this is my production function. Maybe I underline this in white. Yeah, this is my production function per capita. And we all know how the production function per capita looks like. So I have discussed this in previous classes and also on a slide today. So production function per capita is a concave function. So it looks like this. This is what you have learned in Economics 101 in the first economics class. The first derivative is positive. You can see this, the tangent line is positive, but the tangent line here is steeper than the tangent line here, so the second derivative is negative. This is a production function. It's this first component. What is now the blue line? Well, the blue line is the production function times S. The S is the saving rate. That's the component of your income you save. Usually, let's say you save 10% or 20% of your income. So it's a proportion of the income you save. So the S, in other words, is a number between 0 and 1. So if this white curve reflects your income, then S times your income should be below, because it's a proportion of your income. Let's say 10%. So in other words, the blue curve, it is scaled downwards by this S component of your income. So it looks the same, the shape is the same, but it's on a lower level because the S is scaling down the income. It's 10% or 50% of your income. Yeah? So it's in the middle here. You can see that's 50% of your income. So that is how the blue curve may look like. It's, by the way, called the saving curve. And in a closed economy, as you know, saving is equal to investment. You can call it a saving curve or in an investment curve in a closed economy. Now, finally, let me illustrate the red element, the second component of this equation. I already said I will call this the depreciation line. A line is always a linear relationship. Why is this a line? Well, the population growth rate n is assumed to be constant in this simple model. Let's say we have 2 children per woman, constant over time. The depreciation rate is also assumed to be constant. So the capital stock is losing value year by year at a certain proportion, constant. So in other words, what I have here in the bracket is a number, a constant number, times k. K is my variable here. A constant times my variable is a line, and the slope of the line is determined by this constant number. So in other words, the red element here is nothing else as a line which is upward sloping, and the slope of this line is determined by the bracket, the population growth rate and the depreciation rate. And k is my variable. So this second component is like a linear relationship. It starts in the origin. It's a linear line with slope n plus depreciation rate delta, and it's upward sloping because population growth is positive and the depreciation rate is positive. So this can be illustrated by an upward sloping line. So now we have translated this relationship, this equation, into a graph. And what we are going to do in the next classes, we will study the Solow model graphically instead of using this analytical relationship. A final point I want to illustrate in this graphical line is the following. I told you that the blue curve is the saving curve. The red curve is called the depreciation curve. The obvious question in economics is always, do we have an equilibrium? Do we have a point of attraction, a steady state, an equilibrium point? And I will illustrate you in another class this equilibrium point. And actually it turns out that the equilibrium point is the intersection between the saving curve and the depreciation line. So it turns out that this point here will be an equilibrium point. But we will call this a steady state and not an equilibrium. And we will call this a steady state because we have a dynamic model. And that is the first time you have seen and learned about a dynamic model in economics. This point will be our steady state. And this steady state determines my capital labor ratio in steady state. And if we move up to the production function, it determines my income in steady state. So if you're interested in learning more about the Solow model and what is the impact of a change in the saving rate, what is the impact of a change in the population growth rate or in the depreciation rate to the long-run economic development, take a look to the following classes.